Stratis, if you'll turn your mic on.
So can you hear me now? Yeah, sorry for that. So my name is Stratis Karandanelis, and on behalf of the Young Engineering Geologists and the International Association of Engineering Geologists, I would like to welcome you to the fourth series of e-YEG webinars with invited presentations from Professor Hutchinson and Dr. Julian Webber. Firstly, we will start with Professor Hutchinson. Let me give her like a short introduction. Dr. Jean Hutchinson is a professor in geological sciences and geological engineering in Queen's University. She serves as e-YEG Vice President for North America. She's a registered professional engineering in Ontario and is a fellow of both the Canadian Academy of Engineering and the Engineering Institute of Canada. A geological engineer by training, Jean practiced as an engineer for several years, first with the Ontario Ministry of Transportation and later with Crown Crippen Consultants, before joining first the University of Waterloo and then moving to Queen's University. Jean's specialization is in rock engineering, site characterization and risk management for mining and transportation infrastructure, with a focus on landslide hazards and novel monitoring techniques. Professor Hutchinson, will give the floor to you. Please share your screen and you have 45 minutes for the presentation. Thank you.
Good morning, everyone. Stratis, can you hear me okay?
Yeah, I think everything is fine.
Thank you very much. All right, well, thank you so much for your very kind invitation to present this webinar. I have to commend you and the other members of the e-YEG group who are really providing great value within the IAG with these lecture series. So thank you very much for it. Today, I'll be talking about risk-based decision-making considering engineering geology. So to start off, I think a definition is in order. So the reason we do risk-based decision-making is to handle the uncertainties that might prevent the objectives of a project from being obtained. And what we can see on this slide is that within engineering geology, we have some fairly substantial challenges. First, soil and rock have greater variability and uncertainty than other engineered materials like steel or concrete. The quality and accuracy of the geological model that we develop affects our ability to design and construct effectively. The true conditions that we're working with are actually only revealed once an excavation is complete. And engineering projects involving earth materials can fail in many ways, and there are many case histories of this, and also case histories where risk has been managed and handled so that failure doesn't occur. So one of the ways historically that we have and continue to consider uncertainty is by the application of factor of safety. This diagram shows you a case for dam construction. And in this case, they've defined levels of uncertainty in the data, in our assessment, and in the loading conditions that the dam is exposed to, and define a minimum factor of safety for design based on the level of uncertainty, and then the consequence category. So if the consequence of failure is low, significant, or high. And I think it's interesting to note the range of factors of safety when you go from a low level of uncertainty and low consequence to high and high. And their note is that when you get to a high consequence and a high level of uncertainty, you should not do any design until the level of uncertainty is reduced. So the factor of safety also doesn't account for misunderstandings of material behavior, omissions of critical materials and conditions, and poor construction practices. And as I hope you'll see as I go through this lecture, the way of dealing with risk is to try and understand some of these challenges. In general, for slopes, a risk framework can be defined as you see on this diagram. This is highly simplified, but what you see at the top is hazard identification and then an assessment of both the probability and the consequence of failure, leading to a calculation about the risk level. We do an evaluation of the risk, and then we determine whether risk control is required. Important on this is the fact that there's an ongoing assessment and a feedback loop into the upper level of the diagram as time goes on. And you can see in this definition, a risk estimation section, and then a risk management section. When we build this out a little bit, we can see some more detail in terms of identifying the hazards, looking at probability and consequence of failure, looking at evaluation and control. So there are a lot of useful words here to explain risk levels and those sorts of considerations. But I would like to draw your attention to the middle of the diagram at the moment, to the risk calculation or ranking. And so in the middle of the diagram, you can see in its simplest form that risk is the product of probability and consequence. And then we can build that out into a risk chain that I'll describe in a few moments. Really critical in all of this is that communication is ongoing and understandable by those receiving it. In its simplest form, what we're looking at is a combination, again, of likelihood and consequence, or probability and consequence. And you can see in this simple risk matrix from the left to the right, bottom to top, we're getting into more substantial consequences and more substantial probabilities of failure. And the color coding on this diagram is useful because it tells you our engineering response. So if you're in the red zone, you're in an intolerable risk level and immediate action is required. If you're in the orange zone across the diagonal of this very simple matrix, you're in a tolerable risk level. And in this case, risks must be reduced as much as possible. And then in the green zone, you're in the broadly acceptable risk level, where monitoring is required and where risks may be reduced where it's practical to do so. And so this is the framework under which all of the work to do with risk is really considered. This combination of probability and consequence, and what as engineering geologists we do about that. As I mentioned a moment ago, the risk chain assessment is something that is increasingly being used as we get more information and more ability to analyze these factors. So this equation shows you the annual risk, which is the product of 3 factors that give you the probability and 2 factors that give you the consequence. So in the probability, we see an annual probability, we see a probability of that event impacting something, and that the impact occurs when there's a problematic consequence temporally. So if you think about, for example, a landslide impacting a building, if there's no one in the building at the time, there will be a spatial impact, and there'll be damage certainly, but temporarily there will be no lives lost in that circumstance, for example. And then when we look at consequence, we look at the vulnerability of the element and also the element that's at risk. And this can be measured in terms of loss of life, dollars, and/or loss of service. One good definition that I like to use in terms of elements at risk come from this Australian Geomechanics Society publication. And here you can see a series of different elements that could be impacted by a rockfall in this case. And so some of the questions are, what is in the way of the rockfall? How frequently are occupants present, or are vehicles or infrastructure there? And what will the consequence be? How vulnerable is that object to the impact? Another way of looking at consequence of failure is shown here from some work by Chris Bunce, looking at a section of railway track in Canada where he could relate the volume of landslides that occurred to precipitation and other factors. But in this case, he's looking at it from the perspective of service interruption on that railway track. So a measure of the service loss. And he can relate with the 2 lines that he's fit to this data, the effects of the volume of the landslide, the time it takes to clear that and reestablish track service, and then when the trains can get moving again. So another way of measuring consequence. This is another example that seems quite complex, but the reason I wanted to show it to you today is that it's really broken down this idea of a risk matrix into many more levels. You can see a 7 by 6 matrix in this case. And I think what's really instructive is the information that they show about the expected frequency and also the consequences. And they've really broken out the consequences in this case in terms of environmental impact, in terms of financial impact, safety, reputation. And then they've also included some assessment of the volume of a rockfall or slide that would impact their operations. So this is a useful set of comparison between the values of different components. The other really important component of this is shown to the right, where you see catastrophic losses in those categories. And those are situations where the risk is too large, and in those cases, the utilities would be decommissioned. And those correlate to things like loss of consent to operate. And then the final component in this is really thinking about what's an acceptable risk. So if I go back to this one, if we look at this, you can see from green on the bottom left to red on the top right, and something in the middle where you see factors of around 3, which is the boundary between where we must do something and where we should do something and where we don't need to do something, but monitor. And so if we look at this diagram, we can see from 1984 some work trying to compile information about events that had occurred. So this was some of the first work on thinking about risk acceptability. How acceptable is risk? And in this case, Whitman was evaluating previous events as an analog for what society would accept in terms of risk. We see overprinted on this the criterion for dams. And then on the right side, we see the Hong Kong government risk guidelines for the work they do. And many people have adopted this diagram on the right side. This shows you on the x-axis projected number of fatalities from an event, and on the y-axis, the frequency per year of fatalities. And you can see again an unacceptable risk level, a broadly acceptable risk level, and then an area in the middle, which is where you're trying to reduce the risk as much as you can realistically and financially. And when we look at these two ways of thinking about risk and overprint them on one another, I've tried to match them up here based on number of fatalities and the frequency. And so what we see is once you get into thinking about loss of life, you're really getting into those more extreme risk conditions. But in any case, any thinking about risk evaluation, you're always having this decision-making around the types of values to do with consequence and the probability that an event will occur on an annual basis. So now I'll move into engineering geology uncertainty. In this case, we're looking at how engineering geology creates uncertainty in the work that we do. So on the left side, if we're creating an excavation, what's coming next? Where are the critical lithology or structural boundaries located? These give uncertainty in geological conditions. And there are many case examples where site investigation has made it possible to assess some of these ideas, to think about where, say, the major fault is located or where there's a lithological boundary that changes the properties of the material substantially. And it's only really once you get into the excavation that you can really confirm how well you've done with thinking about that. So the level of site investigation and monitoring really impacts the level of certainty you have in terms of your parameters. On the right side, you see the same idea, but in this case to do with the materials themselves. So what are the correct material parameters that you're taking from mapping work you're doing, logging, testing? How many different geological domains should be characterized? And this then gives uncertainty in the representative parameters. And I think it's an important quote at the bottom. Even if detailed assessments of the geological conditions are possible from mapping of the excavated rock surfaces, there remain uncertainties of the mechanical properties to be used in the design. So I don't have time in this talk to go into it, but there's a lot of work being done on the right side ideas where we have enhanced site investigation using new geophysics methods, remote sensing methods. We have new and emerging laboratory testing methods. We have spatial data analysis techniques. These are all important evolutions, but no time today to talk about them. So a couple more slides talking about this source of engineering geology uncertainty. This is a table that I've created from concepts from Still and Palmstrom's paper for hard rock tunneling. And in this case, down the left side, you see the uncertainty level. And then you can see the descriptions related to low, medium, or high uncertainty. And so in terms of geology and ground conditions, in the low case, we're in a clear and simple situation where the ground parameters are easily found and where we have relevant experience related to construction in similar ground conditions. If we move down to the high level of uncertainty, in this case, the geology and ground conditions are unclear and there's known potential for problematic excavation. There's also limited possibilities to assess the ground conditions before the excavation starts. So that defines something to do with the level of uncertainty you anticipate prior to the start of the project. On the right side, in green, you see what happens once you start the excavation. So are the encountered ground conditions good or very good? That puts you into that low level of uncertainty. And as you move down, you see mapping using classification systems. And we heard a great talk in the first e-YEG from Dr. Marinos about that. Then you see in the middle, mapping supported by investigations. And then we saw Dr. Vick's talk following Dr. Marinos' talk about that for large landslides. And then if we move down to the high category, now we're moving from mapping, investigation, and into testing. And this is where we're trying to understand the poor or very poor ground conditions. And then another diagram, the last of these tables, is this one showing sources of geotechnical risk. And I think this one is useful because it talks about the same ideas. Do we have an inadequate understanding of the importance of the ground conditions? And if we do have that, that really affects the upper 5 rows of this table. If we have an inadequate understanding of the importance of ground conditions, we have poor management of the whole engineering geology process. We have poor management of site investigation and contract documentation. We have unreasonable models and design values chosen, and we run into unforeseen ground conditions. If we move down into some of the technical challenges, if we have inherently hazardous ground conditions, that can lead to problems with geotechnical risk. For example, large ground movements or voids, etc. And at the very bottom are the geological conditions that are highly variable. And in this case, often investigation of all of the geological details is impractical. And this leads to the unforeseeable geological details. And if you remember at the beginning, I mentioned that true conditions are really only revealed once an excavation is complete. So we need to be very cognizant of where we are in this spectrum of thinking about sources of risk. So one of the ways we can help with these challenges is developing a ground engineering model. And I've put 2 quotes here that I think are really useful to explain the idea of the ground engineering model. The first is by Perry and others in 2014, and they said, any approximation of the geological conditions at varying scales created for the purpose of solving an engineering problem. So that's why you develop the ground engineering model. And they say for exactly the same geological setting, different engineering projects will require different questions to be asked, different models to be developed, and different types of investigation to be carried out because of the varying interaction and demands of the specific engineering works and the ground. Most recently, in a new paper by Baines and others, they talk about an engineering geological model representing an understanding of the geological conditions that are of engineering significance to the project, and they provide a framework for all engineering geological input to a project and are used to manage geotechnical risks. In schematic form, you see this diagram from Perry et al. You see on the top the engineering geological model development, which is a feedback loop of thinking about conceptual engineering geological model development based on geological information that's created to anticipate what might be encountered on the site. And as you begin to gain information from site investigation and then from doing the construction work, you can observe the geological model, modify it, and create a ground model. And so this, during the site investigation stage, constrains the model in space and time and refines it. And then this feeds eventually at the bottom to an analytical model, which is based on this geological and ground model and is formulated to suit the method you're working on. The key objective is to investigate the potential unknowns. So ground conditions that could be present and which could potentially affect the project, but which have not been specifically observed. And in the most recent paper that's still under publication, they've expanded this thinking. You can see this version of the diagram that I've done here. So you see investigation leading into the model we looked at a moment ago. You can see that within the model, there's an iterative development of the model during multi-stage investigations. And you see that through the flow chart, we have methods of thinking about moving down or returning to get more data. So as we move down from the quality control to design and construction, we're getting more and more data and we're refining our model. And here's some good diagrams showing this evolution of the engineering geology model as you encounter information, as you build this construction. And here's a final model that I'll show you before I move into some of my work. This is one from the Netherlands where they're looking at a proposed tunnel alignment using CPT values to understand the potential ground conditions for that tunnel. So now I'll move into thinking about natural rock slopes. How do we reduce uncertainty for these? We are trying to interpret data from monitoring and instrumentation so that we can understand failure mechanics and processes. We want to develop process models that give us an idea as to the sequence of events and triggers that lead to failure. And this permits us to define input parameters into design, to forecast upcoming events, and to define warning criteria and thresholds. We then use these to think about numerical simulation, which permits us to evaluate the variability and uncertainty of a project and to consider the probability of an event occurring. So the first case I want to talk about is reducing uncertainty by making observations. We're talking about linear infrastructure that's adjacent to rock slopes, in this case, railways in Western Canada. And we have anything from very small failures, such as you see on the left side, to larger events on the right side. The site is located, as I said, in Western Canada. This is one of the slopes we look at. And I just wanted to include some information about the geology. This is a quartzo-feldspathic gneiss with both dioritic intrusions and tonalite dikes. We collect data remotely from different vantage points in this location, and you can see some of these sources of information here. One of the key considerations we have is how frequently we collect data. And as time goes on and more permanent setups that are reasonably priced that permit you to collect this data on a regular or very frequent basis really enhance our understanding. And from this work, we've been able to develop a rockfall database from both point clouds and from photos and observations. This permits us then to do some back analysis of cases that we've seen. So in this case, this is eventually a 2,600 cubic meter failure. And we can see from the change detection, comparing sequences in time of point clouds, in this case from LiDAR, where we see from the top left to the bottom an increasing topple of this spire towards the railway tracks. And in terms of days before failure and the amount of deformation shown on the bottom. And so we can see a topple forming and we can see the rate and magnitude of the movement before failure occurred. And you can see when we look back at the geology, the talus that was generating along the tension crack at the top, displacement that was occurring, and the idea that you can sense the amount of displacement before failure occurs. In this case, we could also do a back analysis and look at rock slope failure precursors. Some of these are as small as 0.1 cubic meter, and you can see a couple of slightly larger events, numbers 1 and 10, and then the eventual final failure. And so as we build these databases of information from these remote sensing techniques, we're able to really start to piece together the history of these failures. Can we see precursors, even if they're very small volumes? Can we see deformation that's giving us an idea that that failure is about to occur? We can also think about it from the perspective of rockfall frequency and magnitude. So here's some work done by Megan relating the geological setting to the rockfalls that we occurred and looking at the frequency magnitude of those rockfalls based on their lithology. And so this helps us to start to manage and think about the engineering geology as it relates to our failure processes. Here's another example showing some close to the track section where we have a series of rockfalls that are occurring. And one of the things that actually was surprising when we put this data set together was, in fact, the spatial distribution of the rockfalls that you can see on the bottom left image. This is a period of about 4 years. And generally, these rockfalls are small enough that they fall into the ditch. And every so often, the maintenance crews come along, remove material from the ditch, and then there's capacity again to store these rockfall events. But when you look at it this way, you can really start to see that there's a distribution of rockfalls across this whole area. And we can see that it ranges in volume from a little over 1 cubic meter to very small volumes. Again, not volumes that really impact the railway operations, but they do start to give us an idea of the processes that are happening on these slopes. Here's some work that's been done to think about structure on slope processes. And you can see the mapping of the structure done by Yannis Farmakis. And you can see how the distribution of the orientation of structures relates to the rockfall processes. And then here in some work done by Paul Mark, you can see thinking about when seasonally these rockfalls are occurring. Are they occurring in winter or non-winter? And you can see from this diagram that most of them are occurring in the winter. So this helps us to think temporally about when these might occur. And what we can see here is some analysis over time of these events done by Paul Mark. And here he's thinking about the number of rockfalls in a given year related to a simplified analysis of the weather, thinking about how often we have freeze-thaw cycles, for example. And you can see a start of a correlation to thinking about this. So again, as we get more information, we can start reducing uncertainty in terms of where will rockfalls occur, when will they occur, and how likely is it that we'll get a certain range of volumes. And then just to finish the story, the other thing that the railways are interested in from this type of work is where event mitigation structures or measures should be placed. And so you can see rock sheds, tunnels, and then these slide detector fences that are located adjacent to ditches. The idea with these is that if an event occurs, it'll break one of the wires on these systems, which sends a signal to stop the trains. And so these are some of the ways that these events are mitigated, and they're always seeking out where and when should an additional mitigation structure or method be put in place. So hopefully you've seen through this section of the talk that we can reduce uncertainty by monitoring. We've had substantial capacity development in recent years in remote sensing techniques with LiDAR and photogrammetry, particularly with the structure from motion analysis techniques. The monitoring we can do with these techniques gives us an unprecedented ability to understand the evolution of slopes. What kind of precursors can we observe? What duration, amount, and orientation of deformation is occurring prior to failure? And I don't have time to talk about it today, but some really interesting work about orientation of the deformation helps you to start to hypothesize the failure mode that you're expecting. And when we couple these data sets with information about conditioning and triggering factors, for example, weather, this permits us to reduce uncertainty in our engineering geology evaluation and lets us focus mitigation efforts both temporally and spatially. I'll now move to some larger landslide risk assessment. So from my perspective, when we're assessing landslides, there are a series of steps that require increasing amounts of information and are increasingly complex to think about. And you can see that on this slide, where initially you have some sense of the extent of the movement, some idea of the rate of movement and velocity on surface. And then when you get into the subsurface, you can start to get an idea of the depth of the movement, the extent of the movement, how much has the sliding surface moved, how our movement changes responding to preconditioning and triggering factors, how far might the landslide run out if it occurs. And if it does occur, do we have the possibility to provide warning in enough time for any people downstream to escape, for example? So one example that I've worked on in the past with Kathy Kalinchuk and Neil Chelland is the Downey slide. It's a slide above the Revelstoke Reservoir, operated and managed by BC Hydro. And I wanted to show this slide, which is uncertainty in the landslide boundaries. Now, this is older information, but originally the main slide mass was shown, as you see on the left diagram, and in intermediate interpretation on the right side, where you see the landslide, which is 3 kilometers by 2 kilometers, showing different sections of main sliding and secondary instabilities. And then once aerial LiDAR became available, and we could couple that with the instrumentation data that we were provided to do analysis on, we could really start to partition this landslide now into a series of different sections, moving in different ways and responding differently to the conditioning factors of piezometric pressure. Another level of uncertainty arises from the fact that in this large landslide, there are several potential sliding shear zones. And so when you're trying to model this and think about risks, you're thinking about the depth to these different layers and what they do in terms of piezometric pressure. So a simplified example here from Dr. Hook of a potential landslide. You can see the geological conditions in this cross section, and you can see the results of modeling. So in this case, a probabilistic analysis where a factor of safety of just over 1 was determined and a probability of failure of about 18%. So in this case, he was able to think about variation in the slide surface location and how that would affect the results of this type of analysis. So in natural slides like you just saw, it's often hard to know exactly where the slide surface is, and you need to do some probabilistic analyses to understand that uncertainty and the potential risk posed. Another is triggering effects, water pressure, or seismic loading. In the right-hand case, I have included this set of pictures from the Navy in Chile, who observed the effects of an earthquake in the Isen Fjord and observed this rock which came down from the mountain and basically skipped across the water surface. So this is a very unique circumstance. And the reason I show this is that this is probably something that most people would never consider as a potential scenario. And one of the things we try and do in risk is think about potential scenarios that might affect our analysis. Here's another set of data from Chris Bunce on his analysis of the slopes in Western Canada. And here you can see antecedent rainfall, 1 to 3 days on the y-axis and 4 to 18 days on the x-axis. And it permits him to think about the boundaries under which landslides do and don't occur to get an idea of the kind of triggering thresholds that might be present in these materials. And then we can bring that into a simulation. In this case, different positions of water table affecting the results of our probabilistic analysis and giving anywhere from a probability of failure of 1% to 21% with a change in the water table position. And then the final part of this is going back to smaller scale processes where we're thinking about simulating rockfalls. And so here's an example again from our Western Canadian rock slopes, where from the change detection on the left side, we can see a source, only 1.4 cubic meters. We can see impact positions down the slope, and then we can see the accumulation of material at the base of the slope. When we take this information from our change detection and also look at the structural geology, we can define a rockfall object such as you see on the right side, which has pre-existing structure along which fragmentation may occur. And when we run these types of simulations, you can see here, we see that the rock falls can fragment along structure or along boundaries that are defined. We can simulate the results of these types of events. In this case, a fragmenting rockfall, where we had information on a precursor basis that this would likely occur because there was a lot of small rockfalls around the boundary. And with this modeling, we can give a sense of what kind of impact there might be on the slope. In this case, it's over a rock shed, so we weren't concerned about the stability of the railway, but it gives a great case of how we can work with this. And this is done using physics engines that have been developed for games. And so one of the things we can do is to think about where the rocks end up. In this case, ditch effectiveness analysis done by Zach Sala. And here he was looking at this fragmental rockfall modeling, looking at where the events ended up. And in this case, the results on the left side are colored on the basis of 95% of the run out. And so the red ones are within 95%, and the blue ones are outside of that. And the blue ones are the ones in this case that would potentially give concern to the railway track operator. And so this is a way of taking this type of analysis from a probabilistic basis to think about how effective a ditch might be. So hopefully you've seen now that we can also reduce uncertainty by simulation. So we're thinking about possible sources of variation in the geological model and the material behavior, and these need to be identified as much as possible in advance. We run numerical simulations using a variety of different methods, considering the geological domains and also reasonable ranges of parameters, and these need to be conducted in order to assess the probability of failure. Future work in this area that is being done already by some people is thinking about a number of things, including partial factors analysis, where we're learning from soil mechanics approaches, breaking down the equation a bit more completely, and reliability assessments as our data sets become more substantial and more representative of what we're finding in situ. So now if I move back to this generic consequence hazard matrix, I'll just for a moment talk about mitigation from the perspective of risk. So in terms of risk, we can think about avoiding risk by reducing the consequence of an event. So this can be by land use planning, by removal of infrastructure, by creating a barricade, for example, a rockfall fence, by bridging or tunneling, or by warning. And warning, I think you've seen from some of the work that's happening with some of these remote sensing techniques, is becoming increasingly possible. But one of the key questions here is the expected rate and volume of failure and whether avoidance is possible. We can also think about mitigation, so to change the hazard level. And in doing so, we can think about putting in drainage for some of the very large slopes, support, excavating materials that are problematic. And the questions here are these technically feasible? How effective would these approaches be? And what would the consequence of failure be as you modify the potential for the hazard? One of the key considerations, in my opinion, is how rapidly the material is behaving. So are we expecting something which is in the extremely slow or the extremely rapid set of categories? And you can see the typical velocities proposed by Cruden and Barnes in this case. And you can imagine that some of these velocities mean that a human response to the movement, even if we would provide warning when these initiate, is not possible. So if you're up in the velocity classes of 6 and 7, it's not possible to have a human response to that without some substantial lead warning. However, in the 4 and 5 category, it is possible to provide warning in advance and to permit evacuation of people. In the slow, very slow categories, these are categories which can be managed by maintenance of those slopes. And so the probable impact of these rates, if warning is not given or warning is not heeded, are that in the non-possible categories of 6 and 7, many lives are likely to be lost and there'll be catastrophic damage to infrastructure. If we move into the orange levels where evacuation is possible, as long as the warning is given and acted upon, then there'll be limited loss of life, but there still will be damage to infrastructure. And then if we look at, again, the maintenance categories, these are cases where there's no loss of life. And if, as long as damage is maintained and repaired, there's potentially no loss of use of the infrastructure, or at least a fairly temporary loss of use of the infrastructure. So I think some of the considerations we have to do with engineering geology models is that we look to the past to gain an understanding of natural processes. And as we look to the future, we have to think about changes in the climate and what those might do to the features we're considering. The increasing development of large-scale geological data repositories site investigation and monitoring information permits analysis of data in 3 dimensions now, but we need a collective effort to store and interpret this data, including collaborative software and data management procedures. And this will support in time increasingly reliable engineering and geological models. And there's some excellent work going on in many of the geological surveys around the world related to these ideas, and a book that's just coming out, edited by Keith Turner, on urban geology models. A lot of work is going on right now related to engineering geology uncertainty and risk. And when I was preparing this talk, I was sort of really struck by the differences in perspective that result from where an engineering geologist is working in industry. In almost all cases, certainly major structures, water pressures, and/or high stresses play a role in the results of the work we're doing. But in the tunneling world, this is, as we know, linear infrastructure, often being constructed in complex and highly variable geological settings with substantial cover, so often very high water pressures or high stresses. So the way that you think about risk and emerging information about the engineering geology has to do with these conditions of linear infrastructure and these challenges. And often, because of the substantial cover, not a lot of investigation at the elevation of the tunnel. So here people rely very much on observing what's happening, using the kinds of things, again, that Dr. Marinos has put together in terms of thinking about challenges and failure modes in tunnels, and permitting us to think about what might be coming and how risky is that exposure. In open pit mining, there's some advanced knowledge of the geological model from a mineral exploration perspective, from all the drilling that's done to prove out the ore body. And there's an increasing exposure of geology in sort of rings as the pit progresses, both in diameter and in depth. And as you get those more substantial depths, you get into circumstances where you can move from relatively small scale failures at the bench level to larger, deeper seated pit wall failures. And so again, quite a different way of thinking about risk because of the way you're exposing the material and what you know about it. And then large, slow moving landslides that I talked about very briefly in this talk. In this case, the site investigation you do is focused on assessing the depth of the slide, the rates of movement associated with different shear zones, and the effects of water pressure. In cases where drainage is installed into the landslide, there's also the follow-up to understand how that water pressure change to do with inputs from climate and outputs with drainage affects the movement and the risk. And the engineering geology model development in each of these cases is really focused on the issues of concern. So as you're thinking about these challenges, it's worthwhile really considering which part of the industry you're thinking about and what kind of information is available and what kind of risk approaches are being adopted, because they're different in each of these cases. In terms of risk acceptance, I only talked about this briefly, but this is another substantial area of future work. Risk acceptability.
Professor Hutchinson, you have 5 minutes.
Thank you. Thank you. Risk acceptability is often defined by company practice, regulations, and/or national standards. But there are certain activities that are deemed by the public to be risky, and these are held to higher acceptance criteria by public opinion. So we see that example around the world to do with, for example, the production of nuclear power and the storage of nuclear waste. Or in Canada, we see it to do with plans to route additional pipelines, where public opinion affects the way we think about risk. And when we run into uncertainty and variability, as we know we will as engineering geologists, it makes it more difficult to convince the public of the correctness of our designs, because we can't say with certainty that we know everything about the excavation. And so these challenges of risk communication are something that increasingly become important to understand as an engineering geologist. So thank you, Stratis, for the time, and thank you very much for your attention to this. I've put my email address at the bottom. The reference list is quite substantial, so if you're interested in that, please feel free to send me an email. And thank you again for the time and the opportunity.
Thank you, Professor Jean. I mean, it was, multi-diverse applications with the term of how we can manage risk in general. So I think there will be many questions. You can provide the questions to the chat session, so Professor Hutchinson can answer some of them. I saw that you did like a lot of work with multi-diverse applications and multi-diverse sensors, such as LiDARs or SAR data. So I think a lot of people is working on the current project on that. Okay, so we have a question. During the last decade, where technology has developed even further, we can even have LiDAR in our phones. Have the alarming level changed at all?
Thanks for that question, Chrysothemis. That's great. Yes, we can have LiDAR in our phones now. Like the newest iPad and iPhone have LiDAR that has a range of about 3 meters and permits you to do very sort of close scale LiDAR surveys. The same thing, in fact, with taking photos with our phones and the structure from motion ability to build 3D models. So both have developed tremendously, and they will continue to do so. The alarming levels, I think they are changing. One of the challenges we have is knowing the rates of movement and the types of failure modes that will give us some idea that an event is about to occur. And so we know some examples in the past where warning was given too frequently, and either in a public situation, people didn't respond when the critical warning was given, or in the case of the railways, if there's too many false alarms, their capacity drops significantly. So in my mind, the challenge is that we have to understand the engineering geology, the failure mechanisms, and put those together with thinking about alarm levels. And so those alarm levels will certainly come along, but we have to have that engineering geology analysis behind it to make it valid. I hope that answered your question, Chrysothemis, but if you have more, you can type. Thank you.
So I think exactly what you said, the integration of remote sensing and with engineering geological knowledge is a crucial part, and that's the link that we have to build better in the future. There is a question says, what programs are used for probability stability analysis? And the calculations are made with the same soil properties to calculate the probability of a failure?
Thank you for that question, Andre. So the probability stability analyses you saw were done with a variety of platforms. Some were done with Slide, which is a rock science piece of software. Some that we do are done with Phases, which is a stress redistribution, stress calculation piece of software. And then in the 3D sense, we've used both FLAC and e-YEG, Itasca software, to think about some of these surfaces. So it depends on whether we're doing 2D, 3D. In terms of the simulation of fragmental rockfall, that has been done in my group with both Unity game engine and an increasingly available one called Houdini. And then your question about the properties, we're looking at ranges of property values. And as I mentioned near the beginning, that's the other half of uncertainty in engineering geology. So where are the boundaries between units, and how do you represent the materials you're working with? And that half about thinking about the materials we're working with, I didn't have time to deal with in this talk, but that's a whole other area of uncertainty. And I see Dr. Day is on this call listening. She's doing a lot of work now on thinking about interblock structure and how that affects the shear strength of rock masses and the behavior of rock masses. So maybe you could invite her at some point, Stratis, to give a talk as well.
Definitely, sure. Okay, so let's have two questions and move on with this next presenter. One question is, climate change with the increase of concentrated precipitation in short periods of time could be integrated in the models?
Completely so, Celeste. That's a really great question. One of the challenges that we have so far in our work is that our our data collection is on a weekly to monthly basis, not a minute to hourly basis. And we see, for example, the work out of the group at Durham, where they're looking at coastal slopes. They can relate constant scanning with the LiDAR system to weather. So certainly we need to think about concentrated precipitation. We need to think about changing antecedent conditions, how much they're affecting our instability. So most certainly we do need to think about that. And I think we can do so as we have these increasingly viable models and understanding of these materials. So yes, I think that's a very, very good point. And it's something that we should all be looking towards in terms of what's conditioning and then triggering these events and more extreme events that can cause these sorts of challenges.
And our last question is, how about the settlement areas from the point of rockfall risk and from the point of uncertainties?
Yeah, so I think if I understand this, the point of the rock fall, you mean where the rock falls are impacting the slope, I guess?
I'm thinking, yeah, kind of, yeah, I relate to that.
Yeah, so we one of the things we've been doing is using our change to see where the rock falls, where the source is. As I said, look where the structure is, and then look where the pieces are impacting the slope, because they tend to remove a little bit of material every time they impact the slope. And so we can see that in our change detection, and then we can see the accumulation at the toe of the slope. So we often will calculate what was the volume at the source, what's the volume added to the cone at the toe, and we can then get an idea whether we've actually managed to see where all the fragments have gone. And so those impact positions give us a really good method for calibrating these types of models. From the perspective of uncertainty, rock mass degradation and rockfall fragmentation, in my mind, is one of the biggest challenges we still have. We don't know whether there's rock bridges inside the piece that's falling. We don't know how much the structure has degraded internal to the rock mass. And so there's an enormous amount of uncertainty in my mind in that particular part of the work. So thinking about how rock falls are liberated, how they will break up as they fall, and how much uncertainty there is in their strength and the presence of any structure internal to them is a big source of uncertainty. So that's one where I think we have a lot of ability to do parametric and probabilistic analyses, but really we have to think about the engineering geology and the weathering of those rock slopes in trying to get at that answer. I hope that answers your question.
I think so, yeah.
Okay, thank you.
Okay, thank you very much, Professor Hutchinson. It was a pleasure to have you here.
Thank you very much.
We're moving to our second presenter, is Dr. Julian Webber, who has over 10 years of experience in geotechnical engineering and engineering geology in North and Central America, Southeast Asia, and Europe. He joined Exponent in 2018 after completing his PhD at UC Berkeley and is based out of Portland, Oregon in USA. Dr. Webber's specialization is in the assessment and mitigation of geological hazards, construction support, and characterization of rock masses. His doctoral research focused on the use of remote sensing technologies to track ground surface displacements related to landslide hazard, which he continues as an affiliate of the Lawrence Berkeley National Laboratory. Dr. Webber also actively participates in various professional organizations. He is the current United States representative at IAEG and the past chair for the Association of Environmental and Engineering Geology San Francisco Bay Area chapter. Welcome, Dr. Webber, and the floor is yours to present your work, please.
Thank you. Let's see.
So yeah, perfect. I think everyone is watching it.
Okay.
Okay, thank you.
Very good. Thank you, everyone. Professor Hutchinson, that's a hard presentation to follow up on, but very, very interesting, and I very much appreciate it as well. So today I'll be focusing a little bit more on the implementation of geohazards assessments for distributed infrastructural systems. And so this is a bit of a more hands-on approach that we perform at Exponent, and is performed around the world, but that I think is a very important take on how we implement a lot of what Professor Hutchinson was just discussing in understanding the hazards, and then applying that to figuring out what the risk of those hazards are to large distributed systems. And I'd like to just take a moment to acknowledge my coworker, Dr. Juan Perry at Exponent, who's been quite instrumental in developing a lot of the work that I'll present today as well. So if you don't know Exponent, we're a very large expert consulting firm, and we focus mainly on, or used to focus mainly on failure analysis. In fact, the company name used to be called Failure Analysis, but now we do a lot of proactive work as well, which is a little bit more what we'll be discussing today. And we're located a little bit everywhere around the world. So if you're interested in a career with Exponent, and I apologize, I have to do this, we're very interested. So a general outline of what I'll discuss today, maybe the purpose of these geohazard assessments, the motivation behind that, what geohazards might you consider, and I'll sort of fly through that to get to the meat of this, which is what is this hazard assessment framework that we've been sort of touching on today. And I'll use the example of pipeline integrity due to surface fault rupture specifically. And then we'll discuss in brief landslide hazards as well. And I'll go over a few recent examples of why this is important. Some examples of pipeline fault creep failure, the application of this framework to road lineaments with landslide hazard, and then some examples for power utilities under wood loading. So the purpose of the primary purpose of a geohazard assessment is to implement essentially the methodology to evaluate potential geotechnical threats to the integrity of an infrastructural system. The methodology can be used to determine hazard zones, if appropriate, or identify remedial measures, ultimately to reduce those hazards. And this is particularly effective for geographically distributed infrastructural systems, such as transportation arteries and large pipeline systems for transmission or distribution of either water or particularly gas, which is explosive. So this is work that's being done, as I mentioned, around the world. In particular, this is sort of an example of a basic application of this framework performed by the local water utility in the San Francisco Bay Area, in which they've really gone to great lengths to estimate the seismic hazard to their system in order to basically ensure a continued service. So the motivation, again, behind establishing a framework for geohazards assessments to these large distributed systems, and East Bay Mud says it well, the utility I just mentioned, is to maintain and improve the district's infrastructure in a cost-effective manner, and to ensure sustainable delivery of their service in a reliable and high quality fashion. So the challenge really is that you have kilometers of system that are aging, and you have increasing service demand as well. And now a heightened risk of existing hazards. With time, we get a better understanding of landslide hazards or seismic hazards. But those are some general outside forces in as far as potential hazards are concerned. But you could also do this in consideration of past performance of your pipelines, corrosion over time. You can establish a framework to consider manufacturing defects, third-party damage, or just improper operation. And again, the benefit to applying this framework is to get better compliance with regulatory agencies and reduce risk, generally speaking, and prevent accidents. In the long run, that'll save a lot of money to these utilities, and everyone will have a much more reliable system to work off of. And ultimately, these systems are very practical for prioritizing how you look at your system. So I mentioned regulations. In discussing pipelines specifically, the Pipeline and Hazardous Materials Safety Administration recently issued what's called the MEGA rule, and basically provides amendments that explicitly require an operator of a utility to identify and evaluate all potential threats, including considerations of seismicity, geology, soil stability of the area of that system. And here locally in Oregon, they developed a resilience 2025 effort. And the idea is to, as Kate Brown, the local governor, would say, to improve our readiness for the Cascadia earthquake and potential tsunami that might follow. And I'll show you what that's about in a second. But the idea here is that integrity management programs need to identify and address the threats to pipelines or other infrastructural systems from weather and outside forces, and incorporate the seismic and the geotechnical and geological amendments contained in the MEGA rule, for example, to improve their systems. So when we discuss geohazards, I think you're all very aware of them. So I'll fly through this a little bit, but I will discuss fault creep today in a little more detail, as well as surface fault rupture and landsliding. And then it's important to acknowledge that there's a multitude of natural hazards out there that we really need to consider. And one of the reasons why Oregon, for one, and I'm using that example since I'm in Portland, is that we have a very significant seismic hazard. On the left here, you can see a historic map of earthquakes, which dates quite far back, actually, here of the state of Oregon, and an active fault map. And what you see on the left of that map is the Cascadia subduction zone. And throughout the state are distributed a number of active faults. And you see a few hotspots with earthquakes, and those are related to volcanoes. But as you can imagine, there's a number of related hazards in relation to seismicity, not just fault rupture or movement along faults. But as you know, the probability of liquefaction is quite significant. And this is just the middle image here is a probability of liquefaction of Oregon map, showing that the central western Oregon and Willamette Valley essentially is very susceptible to liquefaction. And what I like of these maps actually is that you can see the main arteries of the roadways crossing them. So, I've been mentioning pipelines, and I'll focus a little bit on pipelines, but roadways are quite significant here. The main arteries for communication, especially in a natural hazard, are tremendously important. And the question is, how do you look at that as a system to make sure that you can maintain fluid flow and keep it sustainably functioning in the event of a seismic hazard, for example, or landslide. Speaking of landslides, on the right is the probability of a seismic or earthquake-induced landslides in Oregon. And you can see because it's really quite hilly and mountainous region, that's a significant hazard. So you can do these geohazard assessments in sort of a multi-phase approach. And that starts with a preliminary estimate of that hazard and vulnerability or of system performance. And you can, that can be used to scope the extent of your problem and then to identify areas where more detailed studies are needed. And so that's really just sort of your basic beginning to understanding your system, the hazards associated, but it's an important step in that decision-making process. You can take that one step further then and do a more qualitative analysis and implementing these geohazards frameworks, as I'll discuss in a minute. And that'll be oftentimes based on historical and readily available data. You can do this without any site investigation, really, for many areas, especially in the United States, where the USGS and local agencies really have done a significant amount of work that we can base ourselves off of. This information is readily available to everyone. And so you can do this really in a non-intrusive way and get a firsthand sense of the risk to the system that you're interested in looking at. And then finally, ultimately you do a more quantitative analysis characterized by better and more complete data. And that oftentimes comes as from site-specific investigations, but you can do a more a probabilistic or deterministic analysis of your issue at hand, and then likely include for pipelines, for example, the segments that might be of high consequence or high risk. And I'll show you an example of that in a minute. So I keep mentioning pipelines, and I'm going to get a little more specific here as examples, but so, what are some of the geotechnical threats to pipeline integrity, simply put? And in looking at surface fault rupture and landslide crossings, I think you can all imagine that the pipeline will behave in many different ways due to movement, and that might be buckling, that might be extension. And the question is, under this loading, what is the serviceability of your pipeline, and what does that depend on? So I mentioned this phase approach, and what you'd start off by doing in this case, for example, is looking at your system in segments. You define your pipeline segments, and then collect all the data you can related to it. So that might be geomorphic data, that would be geologic data, that would also be project data. So the understanding the actual system itself, what is it comprised of? Then you can perform this geotechnical hazards assessment, as I've been discussing, and you can produce based on that a sort of a report of what is the hazard level of each of these segments that you're interested in. And you can provide based off of that some conceptual remedial alternatives. And then the next step, as I mentioned before, is to get a little bit more detailed, and you might do site-specific investigations, which would produce geotechnical data reports, for example, and then do more geotechnical analysis and alternatives, but and produce an evaluation report based off that for remedial design. So fault rupture hazards specifically, I hope you're all familiar with this, but I think it's important to acknowledge that that each of these terms in engineering geology are quite basic. I mean, we understand them conceptually, but it's about how they're understood by the regulatory agencies and how they're understood by your clients or the system owners. And so these different terms might take some slightly different definitions. And so it's important to understand that, you know, a fault is a fault, but a fault zone is a congregation of faults, as you know, but it may be different thicknesses, and it really depends on the type of movement you might expect along that fault. So we'll get involved oftentimes as engineering geologists to define this in a better way. You know, it's important to draw some limits there so that we can really constrain the issues that we're looking at. Now, there's a lot of administrative language out there to define what might be an active fault, for example, what might be potentially hazardous faults. And unfortunately, that sort of leaves us wide open for understanding, you know, in day-to-day terms, what is the true hazard at hand. And just as some examples, the state of Oregon administrative rules identify active faults as being Holocene, so less than you know, 11,650 years or so. That's not always the case, and specifically in Oregon as well, the Department of Geology and Mineral Resources also identifies potentially hazardous faults as having been active within the last 1.6 million years. So we're left with having to make some educated, I hope, decisions on for if you're looking at fault crossings or if you're looking at seismic activity in relation to your system, understanding what is your actual hazard and what is something that you truly need to consider and what is something that is maybe beyond the service lifetime of the system that you're considering. And so it's not to say that it might not happen, but again, this is the discussion that happens with your local authorities and the system administrators to understand what is their level of comfort and what is the risk they're willing to assume based on these different hazards that exist. And obviously, if you consider anything that's moved in the last 1.6 million years, you're going to have a lot of remediation to do. Other states like California also have a little bit more specific terms through the Alquist-Priolo Act of 1972, for example. And in that case, they define specific fault zones related to well understood active faults and define them as being a minimum of 30 meters wide. But that extends to anywhere up to about 150 meters on either side. So discussing surface fault rupture, and you may have heard of this. Recently, in 2009, we had the Ridgecrest earthquake, which was a 6.4 left lateral event and caused a significant amount of surface fault rupture. And if you're not familiar with the Geotechnical Extreme Events Reconnaissance Association, you should be. You can look them up online, and they're basically a consortium of researchers and consultants who respond to these hazard events to collect all the data we need to be able to advance our science. So these are just some example photos collected by Exponent and from the GEAR report in relation to the 2019 earthquake. And what you see on the right is obviously the effects of surface fault rupture in relation to a water line specifically. Now, what I'd like to point out here is that not all pipelines are created equal. And this is another image from the GEAR report specifically, showing there was significant surface fault rupture throughout the region, but not all pipes broke. And it really depends on what the pipe is made of ultimately. And this is where you start to define qualitatively, not just qualitatively, quantitatively, what is your system made of? And what are the different components of that system that play into the hazard related to failure? And so, the risk related to failure in relation to that hazard. So Some sections of pipeline, as we see here, just deformed with movement. Oftentimes, in this case, they were steel pipes, and they had basically was a long seam along them, and really quite high grade steel. They were relatively recently installed. They weren't too old pipes. And they had a fairly large, this is in inches, I apologize, but about 11 inches outside diameter with a moderate wall thickness. Now, I'm pointing these things out because this is what matters when you're looking at a pipeline. Specifically, the age matters, the diameter matters, what is it made of, and what is the wall thickness, because those all define its capacity to sustain deformation. So in relation to pipelines, what you might do, for example, is a segment categorization to sort of drill down in understanding what are the portions of that pipeline that are at risk specifically. And so you want to understand the relative likelihood of failure throughout the system, and you want to do it in a simple way, but quantitative, that you get what you need out of it. And the image on the right is the Hayward Fault zone in the San Francisco Bay Area, with a typical water line, for example, drawn across it. So you would identify, as I mentioned earlier, input parameters. And based on those input parameters, you might establish what I'm calling indicative factors. And so those are each of the different parts of your system that need to factor into the understanding of the relative likelihood of failure. And based on those indicative factors, you can calculate what I call a relative hazard factor. And that's simply just a weighted function of the indicative factors. And then what you can do is work with your local agencies, for example, to establish a general comfort or acceptance of risk, and identify what might be, based on that hazard factor, a low hazard level, a moderate hazard level, or a high hazard level. And what's important to acknowledge as well is that there's a lot of parts of these systems where you just won't have enough data. And that's something that really needs to be acknowledged, because that will trigger further investigation. So I mentioned these weighted indicative factors. What are they based off of? Well, as you might imagine, for example, likely fault displacement. How much displacement is one thing, but what is the likelihood of displacement in the first place? And so that's going to be an important hazard factor, and it'll probably be weighted against a lot of the different modes of failure that you'll consider in your system. As far as the system itself is concerned, you're going to be interested in, if it's a pipeline, what are the section details, its diameter, its thickness, its material. What are the anchoring points along your system, and where are they located with respect to the alignment of your suggested fault? Is that fault well defined, or do you need to define a fault zone that will essentially make the area of interest much larger? Again, when was this pipe installed? Installation methods and materials used will make a very big difference in the likelihood of failure. And what is the incidence angle of crossing, for example, because that is going to dictate whether this pipe, for example, would fail in compression or tension. So you can sort of do this ad nauseum with many different parts of your system. The point is that you can do a semi-quantitative assessment of your system based off of each of these components, and then bring that back to what is sort of, I think, elegantly a qualitative assessment of your system. So you put them all together, create a hazard factor, and then decide, for example, if my hazard factor, which might be out of 100, is, if my hazard factor is anywhere between, 90 and 95, that I would consider very high hazard. And then so you can work with the regulators and the system administrators to identify those levels of interest, and then that would trigger either monitoring, as Professor Hutchinson was discussing earlier, or actual remedial design and measures. So I've been talking about surface fault rupture, and I've been talking about pipelines, but I think it's important to acknowledge that there's not just one type of hazard. And I mentioned landslide hazard, and this is simply an image of the same area, the San Francisco East Bay Hills, and it's a landslide hazard map of the hills, and as you can tell, these pipelines are distributed all throughout. There's some really important transportation arteries that cross it as well. And so it's not just about this, whether, for example, the Hayward Fault will rupture and when, but also what are the landslides doing around it? And landslides, as you know, have different failing mechanisms. They can be earthquake induced, but in this case, for example, you can refine the available data on that hazard to look at different modes of deformation. So I mentioned slope creep earlier, and in this case, for example, and this is a shameless plug for my personal research, that you'd have you can define areas of larger displacements over time, and you can basically see from this animation that these landslides that I've identified with precipitation tend to accelerate, and they don't do that equally. They do it in really quite a heterogeneous sense, but parts of those slides are really quite active. And what you see flashing in this animation are pipe breaks over time as well. And what you find is a lot of these pipe breaks are actually very closely related to the margins of the landslides, as you might expect, but also from heterogeneous deformation within the landslides. And in this case, movement is very much controlled by precipitation. And as you can imagine, ultimately, if there was a large enough earthquake at the right time, things would move in a more cohesive fashion all at once. So this is another example of how you can apply an existing hazard, an understanding of a specific mode of deformation. And again, all the different components of your system and how they cross this hazard, the orientation, the modes of failure, et cetera, the sense of movement, to again inform the understanding of what that hazard factor might be for each of the segments you're interested in, and then prioritize your system based off of that. Now, I'd like to acknowledge that there's quite a few other ways of looking at this. And this framework I call semi-quantitative. I mean, it's really truthfully, it can be as quantitative as you want, depending on how you understand the probability of failure of each part or each component of your system. But it offers ultimately a practical qualitative evaluation of risk. And a more formal quantitative alternative is the use of fragility functions. So you can estimate the return period of your hazard, essentially, and from that you can convolve these fragility curves of either the component themselves or the system as a whole. Ultimately, you can combine every component for the system. And these fragility curves are a function of the probability of component failure with respect to the occurrence of your loading. And that's actually specifically what East Bay Mud I mentioned earlier has done for their system. With that, I'm going to move to a few examples, and I'll start again with pipeline failures and fault creep. And this is a great example of a 60-inch pipeline break due to long-term fault creep along the Hayward Fault. And this failure occurred in 2011, and again was in a zone that was well understood to be moving, but the rates weren't fully understood, and ultimately failure did occur of the concrete 60-inch line that was installed. And to avoid further deformation in the future and breaks, they wouldn't avoid deformation, but to mitigate some of that deformation, they installed a high density polyethylene line with a flexible joint system to accommodate for continued movement. So these are examples of ways you might mitigate the issue, but understanding that that issue exists in the first place is really quite important. Another example, and I'll be a little vague about this, I apologize, but is also in the East Bay Hills, a creeping zone of the Hayward Fault resulted in rupture of a gas line, and ultimately a car passing by ignited that gas at the surface of the street, and you had quite a mess, unfortunately. But with a little bit of investigation, what we found is that really this was entirely related to fault creep over time, that an elbow in that pipe had failed due to the right lateral deformation and distributed deformation across the line itself and over time. And so this is something that really could have been avoided had that been understood in the first place. Another example is how you might apply this to landslide hazards and long transportation artery system planning. And so this is an example of some landslide hazard mapping that I performed for a roadway going through a tropical jungle. And as you can imagine, there's quite a bit of complexity involved in trying to understand where landslides might be in a very densely forested environment. And so simply put, we established in this case a general understanding of what these landslides, what their morphology is and whether they are certain or not. And so we looked at our hazard and broke it down into different components to understand what the different types of deformation are and how they might affect the alignment of the roadway specifically. And then we were able to break down parts of the roadway itself to understand, based on this hazard and the potential for occurrence, which areas might be of interest to study specifically. And as Professor Hutchinson mentioned previously, you can apply a tremendous number of different remote sensing methodologies. And so I showed you my research, which was INSAR measurements of ground surface deformation over time. This is simply a very high resolution LiDAR imaging of the ground surface. And what you can see here is immediately you can point out areas of potential landsliding. And then based off of the categorization of the road alignment in the first place and different parts of the alignment, which might be more important than others, you can then go out to the site and either verify or do more detailed investigations, or you can simply account for them in your road design of road cuts. And this is why this is so important. This is the active road cut and what triggered very much the investigation that we performed. As they were performing these cuts, they were going to be installing a culvert, and that triggered a very large landslide. And this is a problem because now you have a lot more soil to move. Now you have to redesign part of the roadway, and now you have an existing hazard in the future that might be a continuous problem for not only the culvert but the roadway itself. Apologize. So another example is public safety. So you've probably heard a lot about the fires that have been occurring in the state of California and along the entire West Coast of the United States lately, and that a lot of them are triggered by power line shortages or ignited through power lines that either break under wind loading, for example, or sparking from cross lines. And the question for the big utility companies, which have these very, very sprawling distributed systems throughout the states, is where do you shut power off? And when do you shut power off, under what conditions? And that, I think you can imagine, is a very difficult decision to make, because it involves quite a bit of money ultimately, and aside from the bad press. So how do they make that decision? And Professor Hutchinson mentioned the sort of what I'm calling a traditional way of evaluating the infrastructure risk is these hazard matrices, so to speak. And so that's a really practical way of translating the qualitative, in a qualitative fashion, the risk to your system and what parts of your system land where, based on what you're comfortable in accepting. But as I mentioned earlier, you can also look at this in a more quantitative way with with the fragility curves. And those fragility curves, for example, you can understand what is the annual exceedance of wind loading, and then use that to develop a probability of failure due to wind loading on your system. And in this case, it's exactly what we've done. And what you can tell is ultimately a new system, new infrastructure will have a steeper curve, so to speak. And basically, for example, a probability of exceedance for 100-mile-an-hour winds might be 10%. For a 10% probability of failure, you might have 100-mile-an-hour winds for an older infrastructure system versus a newer infrastructure system, which would be more resilient. And it's really important to understand your system and each of its components, as I mentioned earlier, to be able to establish this and then understand what is the level at which you're comfortable continuing to operate your asset. So your risk tolerance for operability assessment decision might be, for example, that you don't want to accept a probability of failure of anything more than 10 to the minus 4, which is very small, obviously. But in this case, it's really important asset. So what is the risk you're willing to tolerate? And so for your different system, for your understanding of the condition of your current system, you might find actually that if you don't want to assume any higher risk than that, you'll have to shut your system off at a much lower wind speed in this case. Versus when you first install your system, you know that the system is new, you know that it's resilient, you know that the structural components are, minus errors in fabrication or installation, are more resistant to deformation. And so you might be able to tolerate higher wind loads. But that's something that's really important to understand, and you can translate in understanding the full probability failure with respect to these hazard curves. So I guess in summary, I think these geohazard assessment, this geohazard assessment framework is really fundamental in identifying the threats to the integrity of your existing infrastructure systems. And the multi-phase approach that I've discussed today is really a powerful tool to maintain and improve your infrastructure in a cost-effective and sustainable manner. For any given hazard, and understanding of that system's characteristics, you can have essentially a systematic qualitative and quantitative understanding of risk to that asset, whether it be done through fragility curves or the hazard factor evaluation that I discussed. So really importantly, regulatory changes today are making this type of assessment a requirement, and in multiple industries. So, I've used the example of pipelines and briefly roadways and power transmission lines, but I think you can imagine this is pretty broad reaching. So as illustrated through the examples, I hope you've seen that these are particularly effective methodologies for geographically distributed infrastructure systems and understanding that there is a risk. And the question is, how do you handle it? Now, I mentioned, you can do this for quite a few different under quite a few different realms, so to speak, and we do that specifically as a company for many different utilities and different levels, looking at the risk assessment of your system and just integrity management, et cetera. But that can extend really quite far, even as far as human performance consulting. And so with that, I thank you all for your attention. I've included my email here for questions if you like, and I'll take any questions.
Thank you very much, Dr. Webber. I think it was a really informative presentation. So we have a couple of questions already. So who is defining the value of acceptable risk? For example, for pipelines, is it made by the owner of the pipeline or is it made by geotechnics, geologists? And the second part of this question is, are you mostly use qualitative or quantitative risk analysis in your work?
So the first part of the question is, it depends. It's preferably a educated and informed conversation between the owners of the system and the geotechnical consultants or geologists that are hired to understand, better. First of all, the geotechs and the geologists inform the client as to what that hazard is and what the probability of occurrence is related to that hazard, and then help the owner of the system to define the level of hazard they're willing to accept. Now, legally, there are levels of hazard that they're allowed to accept, right? And that's in part informed through the regulatory agencies, like I mentioned, the mega rule earlier on in the presentation. And so, there are guidelines there, but hopefully that decision is one that's taken through extensive discussion and understanding of the system and the hazard itself. And at that point, the utility can make its own decisions. Ultimately, they're the ones who make that decision on what level of hazard they're willing to accept, because ultimately they'll be responsible. The second part of the question is whether we do qualitative or quantitative. And I guess ultimately as a consultant, it's all about the money. So it really depends on what your client is willing to pay for. And so we oftentimes will start with a more qualitative approach to give the client a understanding of the hazard and the the risk to their system, and what parts of that system are at higher hazard than others, and then usually encourage that client to do a more qualitative assessment of that system, which can involve some really quite extensive modeling, for example, and that'll get expensive fast, obviously, because it's not, everything needs to be done, unfortunately, in the consulting industry yesterday and at a PhD level. So it's not a simple problem to get around, but it can be quite effortful and expensive. So.
We have one more question from a special attendee, Scott Burns. On your landslide map of the Hayward Fault, what defines the difference between your red landslides and your green landslides?
Oh, the hazard, the yellow landslides, I think you mean, and the red ones. So that's a local consultant, Alan Kropp and Associates, through 30 or 40 years of consulting experience, has developed that landslide hazard map locally through his own projects. And so the red slides are slides known to be actively moving. And the yellow slides are these, which are generally associated to the smaller red ones, are these larger deep-seated paleo landslides, which there's some discussion as to whether or not they're actually actively deforming. But I found with my research that they don't move much on an annual basis.
Okay. I think we don't have any questions until now. I would like to invite once again Professor Hutchinson to say on behalf of the young engineering geologists, we would like to thank you for accepting our proposal and being our distinguished speakers. It's really valuable for us. I hope all the attendees really enjoyed today's session, and we hope to stay tuned for the upcoming actions. Once again, thank you, Dr. Waeber. Thank you, Dr. Hutchinson. Thank you all for being today here. Stay safe. See you.
Thanks for the opportunity. Bye.
Thank you.
Bye.
Thanks.